have the pleasure of welcoming Professor Jiun Haw Chu to be with us virtually from the University of Washington. And Jiun Haw obtained his Bachelor of Science degree from the National Jiao Tong University in Taiwan in 2004. His PhD degree from Stanford in 2012, and where he obtained many very beautiful high-impact work on the subjects of iron-based superconductors and topological materials. And then he did his postdoc work at both UC Berkeley and Stanford, working on iridates and other quantum materials before joining the University of Washington as an assistant professor in 2016. Jiun Haw has since then won numerous awards, which include the Young Investigator Award from the Air Force, the Moore Fellowship in Material Synthesis, the Sloan Fellowship, the Pecker Fellowship, and the Presidential Early Career Award last year. So basically everything you can possibly get as an assistant professor. Jiun Haw is also a pioneer in studying nematicity in a variety of quantum materials, and he is one of the very first people to develop experimental techniques for tuning nematicity from the beginning mechanical clamp type devices to in situ tunable piezo stack devices, where he's shown beautiful work on how to extract quantities related to nematic susceptibility. And that is the subject at which he will tell us about today, and in his talk of nematic quantum criticality in iron-based superconductors. So, so I guess Jiun Haw, you can take it. We can, yeah, carry from Jiun Haw. And if you have questions, you can, I guess, type in the chat if you want to, which I will try to keep track of. So.
All right, sure. Thank you very much, Ming, for the very generous and kind introduction. And yeah, it's a great pleasure to give you this talk virtually, and especially in front of the world leaders in this field. So, so what am I going to talk about today is a story about two remarkable findings near the nematic quantum critical points of the iron-based superconductors. So the first one is that we find out that the superconductivity near this nematic quantum critical point is extremely sensitive to strain. It's so sensitive so that, for example, for this underdoped compound with 13 or 11 Kelvin TC, you can fully suppress the superconductivity. The TC can extrapolate to 0 with within 1% of strain. And obviously, this has something to do with nematic quantum criticality, but it also implies that there's a very strong electron lattice coupling in this material. So in order to further investigate that, we developed a new experimental technique, which I temporarily call this elasto XRD, elasto X-ray diffraction. So this is basically a combination of in situ strain tuning with the X-ray diffractions, so that we can, using X-ray to extract all the structural microscopic information, such as lattice constant, twin populations of the crystal while we're strain tuning and then doing the resistivity measurements. So from this kind of measurements, we can very precisely detune the crystals and then extract a quantity that was not being able to, kind of measure before, but now we can measure it with a much greater precisions. And this quantity, which we call it a spontaneous lasso rescue coefficient. It's basically the spontaneous resilient isotropy divided by the spontaneous lattice distortions within the nematic phase. And we believe that this quantity is a way to measure the electron lattice coupling of the materials in the nematic states. And then what we find out is that this quantity actually increased significantly as we approach a nematic quantum critical point. It's basically increased by almost 4-fold. And so this is basically telling us that even though when you're suppressing the nematicity in these materials, the electron becoming more and more sensitive to lattice, and then possibly to do with this high temperature superconductivity in this material. Okay, so before I begin the full talk, let me acknowledge the people who actually do this work. So these works are really driven by my students, Joshua Sanchez and then Paul Manilowski. So Paul had did most of the works on the suppression of superconductivity, and then Shua is really the driving force of this development of elasto X-ray diffraction. And for the elasto X-ray diffraction, we're also working closely with the Phil Wright and Jung Woo Kim, staff scientists in the APS of Argonne National Lab, as well as Jen Liu from University of Tennessee. Okay, so this is the outline of my talk. I'm going to give an overview or background on the nematicity and superconductivity in iron-based superconductor. And then I'm going to turn into the extreme sensitivity of superconductivity to strain, and then finally the new transport coefficient. So starting from the first. So let me begin with the phase diagram of the two kind of high TC superconductors we have so far. So on the left is the phase diagram of the iron nictide, iron-based superconductor, the prototypical iron-based superconductor, cobalt barium iron tungsten 2. And the right-hand side one is the YBCO, the cuprate. So at first glance, this temperature and then doping phase diagram looks rather similar for these two high-temperature superconductor. You have a magnetic symmetry breaking phase at the 0 doping, and then as you tune the doping and suppress this magnetic symmetry breaking phase, and then superconductivity emerge. And this magnetic symmetry breaking phase is an anti-ferromagnet. Now, this certainly motivates the consideration of spin fluctuation as appearing for the superconductivity in both class of materials. But if you take a further look, then you can start to see the difference. For example, in the iron-based superconductor, the antiferromagnetic phase actually forming a collinear antiferromagnetic order that breaks the crystal C4 symmetry. The iron spins are aligned ferromagnetic along one direction and then aligned antiferromagnetic along the other directions. And this nesting wave vector is this ordering wave vector has a special implications when you're considering the Fermi surface of these materials. So this is another difference between the iron-based superconductor and the cuprates, where the iron-based superconductor is a multi-band materials where the cuprate can be quite well described by a single band Hopper model. Now for the iron-based superconductor, you have at least 2 hole pockets in the zone centers and then 2 electron pockets at the zone corner. And this ordering wave vector naturally nests this the electron and hole pockets. So again, this kind of nesting wave vector motivates the consideration of spin fluctuation, creating this S plus minus superconducting states. So this seems to be the end of the story, but if you look further closely into the phase diagram, then you realize that there's actually another phase appearing on top of the antiferromagnetic phase. This is this green region here, where there seems to be a phase transition separated from the magnetic phase. And this phase is the so-called nematic phase, which in some sense, you can think of it as a melting of the spin density or melting of the magnetic stripes, where the system can break this symmetry sequentially. So first, you can break the C4 symmetry and lowering the symmetry to C2 by developing a spin fluctuation and isotropy. For example, at the tetragonal paramagnetic phase, you have spin fluctuation both along the X direction and Y direction, but once you enter nematic states, the fluctuation is stronger along one direction than the other. Then once you develop this nematic phase, when you further cool the system, then finally the system breaks the translation and time reversal symmetry. So this nematic phase is actually the so-called Q equals 0 symmetry breaking phase. Namely, in that phase, there's no translational symmetry breaking. The order parameter is basically a physical quantity that is uniform across the space. Now, this kind of rotational symmetry breaking phase is by symmetry. It will be linearly coupled to the lattice. Some of the lattice distortion lowering the crystal point group symmetry. So in the tetragonal case, then this is corresponding to a orthorhombic distortion. And then indeed, when you do the measurements, X-ray diffraction measurement, measuring the crystal lattice below the nematic phase transition, you can see the orthorhombicity, which is defined by the A lattice constant minus B lattice constant divided by A plus B. That develops below the phase transition, following like a mean field behavior. And what is really interesting in this pioneering work by the Iowa State group is that they find out that this structural transitions, actually the lattice distortion is being suppressed once the system enter into the superconducting phase. So this really implies that the superconductivity is actually competing with the orthorhomicity and then with the structural distortion. And then the structural distortion is really just a secondary order parameter that follow the primary electronic order parameter, which is really the driving force of the phase transition. So this linear coupling between the electron nematicity and then the orthorhombic distortion also allow us to do another kind of measurements, which is called the elastoresistive measurements. And these measurements turn out to be a very powerful way to probe the nematic fluctuation or probe the nematic susceptibility of the system. And the idea is following. Now, if we treat the receipt and isotropy as a proxy of the nematic order parameter, since they transform the same way. So in this tetrahedral point group, now at least you expect that they will be linearly proportional to each other in the infinitesimal level. Then when you're measuring the induced resistive anisotropy by applying a controllable anisotropic strength above the phase transition, then you're effectively measuring the nematic susceptibility. Now, this is the same way like you're measuring the magnetic susceptibility of a ferromagnets, where you're applying a field and measuring the induced magnetization. Here, you're measuring the nematic susceptibility by measuring the induced resistive anisotropy by an isotropic strength. So in practice, you're gluing a crystal on the sidewall of a piezo stack, which will for example, like elongate it along this direction and then contract along along this direction if you're applying a positive voltage along the pulling direction. And by putting the contact on the corners of the crystal, you can very precisely extract the resistive anisotropy, decompose the resistive tensor, and then find out that resistive anisotropy is indeed linearly responding to the anisotropic strength. And then by fitting a slope, then you can get this quantity of elastoresistive coefficient, which is proportional to nematic susceptibility, and then showing a divergent behavior as you're approaching the phase transition. Now, one thing I want to point out, and which will be useful later, is that if you look closer, then you'll find out that this elastoresistive coefficient, although having a divergent 1/T temperature dependence, but it actually doesn't reach a infinite value as you actually sitting on a phase transition. So this is unlike the ferromagnet, which you do believe that this magnetic susceptibility will diverge at the critical temperature. Here, the reason is because the quantity we're measuring is not the true susceptibility of the whole system. This is actually measuring the Beer susceptibility. This is a susceptibility as if the system is sitting on a fixed rigid lattice. You kind of turn off the electron lattice coupling and then see how this electronic system diverge. And then once you turn on this electron lattice coupling, then the actual phase transition temperature will actually enhance from the divergent temperature of this Beer susceptibility. And then this is just because that this lattice is acting like a polarizable medium. Therefore, you don't need to actually fully diverge your susceptibility in order to reaching a phase transition instability. So this is just an important fact about this elastoresistive coefficient, which will be quite helpful when we are discussing these spontaneous elastoresistive coefficient in the later part of this talk. So in any case, we find out that this nematic susceptibility diverge. I mean, this is kind of also another evidence of the system is driven by electron nematicity. The structural transition is driven by electron nematicity, and then you can measure that across a wide range of doping of these materials. And if you plot this elastoresistive coefficient in a color map, then what you can see is that this elastoresistive coefficient has a strongest intensity near the optimal doping. And then in fact, if you plot the superconducting TC versus the maximum value of the elastoresistive coefficient of a range of iron-based superconductor, including the phosphorus doped, the nickel doped, the iron chalcogenides, and then a few cobalt doping, which is these black dots, that you'll find out that there's a nice linear correlations between the maximum of the nematic susceptibility and the TC of the material. This certainly kind of implies that the nematic susceptibility or the nematic fluctuation could also be beneficial or even responsible for the period interaction in this material. So this kind of idea is not only driven by experimental observation, but there's also a few theoretical works kind of pushing forward this idea of nematic quantum critical fluctuation could help to boost the superconductivity in every period channel. Obviously, the question is, can we directly test this idea? Is there a way that we can control the fluctuations and then see, for example, like TC changes if, let's say, we turn off the fluctuation? And to put it into a broader context, if you look at the phase diagram of
Jiun Haw, can I stop you? Do you mind?
Sure.
So this issue of T star being different from TS, I agree with what you said and you've analyzed before, but I wonder just, and also it sort of brings the T star sort of closer to T nail, which is interesting. compared to TS
Mm-hmm.
to T-nail curves, at least on this plot. But in principle, there's a second way, which is that the transition could be first order, in which case this T star parameter that you get from, I guess, some kind of Curie-Weiss type of fit, right?
Mm-hmm.
Of the nematic susceptibility would
Mm-hmm.
also be different from TS. So I just wonder how much, I think in some of these materials, at least there's some statement that the structural phase transition is first order. And I just wonder how much affects maybe just the details, but is there some
My
way
understanding
that's
is
coming to
that
play?
the structural transition is first order. I think at least my understanding is that even for the parent compound, the structural transition is second order. However, the anti-Fermat transition is first order within this doping range. So what happens is that you have a second order transition of the structural transition, and then your order parameter grows continuously. And then when the anti-Fermat order set in below 1.6% in cobalt doping, then you have a sudden jump of the structural distortion, which is coming from the first order nature of the anti-Fermat transition. And then this first order transition eventually becomes second order after it passes, I think it's tricritical points around here. So I haven't really, in this analysis, we really didn't put in the anti-Fermat instability into the system. So I'm not sure how that first order transition will affect this analysis. And then and then there's also some issue or controversy of what is the T star determined by different techniques. There are T star determined by usually what we at this in the past experiment, what was found out is that the T star extracted from the shear modulus or from Raman seems to be much lower compared to the elastoresistivity. So hopefully in the second part of my talk, what I'm going to show you is that we not only measure this strain resistivity behavior above the phase transition. Now with this elasto XRD, we're also measuring a strain resistivity behavior below the transition, where everything is spontaneously,
I see.
And then with that, then we can actually do some quantitative comparison between this ratio below and above the phase transition, and then they match. And then so I think this degree of agreement is kind of saying that first of all, the resistivity is actually a really good representation of the loop parameter, and then also this mean field actually work extremely well for one reason or another. That I don't understand.
Sure. I mean, if you have information from two sides, that's beautiful. Yeah. Thank you.
So for phosphor doped stuff, I mean, because the structural and magnetic phase transition are completely coupled, right, at all doping levels. So, so really, this in principle, can't have a second order phase transition, right? It has to be a first order.
That's right. Yeah, you're absolutely right. I totally forgot about phosphorus though. But okay, so I cannot comment on how that will impact on the analysis. But what I can say is that we have also measured the elastoresidual coefficient of the phosphorus doped over the whole doping range, and then at this in this part of the phase diagram. And it looks just like the cobalt dope. Like you can the temperature dependence of the elastoresidual coefficient also like a Curie-Weiss like, and then the T star is also 10 or 20 Kelvin just below the combined first order structural magnetic transitions. So at least in the lighter doping, everything seems to work very well. But it's quite strange. It becomes quite strange around optimal doping, where it's quite tricky. It's kind of related to all these issues and controversy about whether there's a nematic transition above the phase transition. But I can discuss with you offline and share you some data. But this won't be covered in this talk. Okay, right. So at least there's some interesting measurements on the nematic susceptibility, which indicates, there could be some correlation between the superconducting TC and the nematic fluctuation, and then we want to directly test that. So, and then in a broader context, if you look at the phase diagram of a lot of this high TC or unconventional superconductor, they all share a rather similar phase diagram where some symmetry breaking phase is suppressed and then superconductivity emerged. Now, here is the hyperintercalated transition metal dichalcogenide. Now, this is iron-based superconductor. This is the organics phase diagram controlled by pressure, and then this is the heavy fermion controlled by pressure. And if you just step back and then from an outside point of view, they all look really similar. Then obviously, if we can all do this experiment of controlling the fluctuations and then see how the TC change when you applying when you're controlling fluctuation, then that would be great to test what's the parent mechanism in these materials. Now the problem is that if you look at the symmetry breaking phase in all this material, they are all breaking translational symmetry, and first of all, a simple idea is that if you can apply a conjugate field, just like applying a field to a ferromagnet which align the fluctuation moments, then you can suppress the fluctuation, and supposedly you should suppress the superconductivity. But the challenge for all these other superconductors is that the symmetry breaking also involves translational symmetry breaking. So therefore, you need a spatially modulated conjugate field to suppress the fluctuation. And unfortunately, for the pnictides, you have this, or the iron or the chalcogenides, you have this nematicity, which is a Q=0 symmetry breaking field. So therefore, it's probably the most easiest one to applying symmetry breaking field and then suppress the fluctuation and then observe its impact on superconductivity. So I think in this sense, the nematicity in iron-based superconductor is kind of a very unique case that can allow us to test this idea of competing symmetry breaking phases and the fluctuation of symmetry breaking phases for superconductivity. Okay, so I'm going to finish the introduction, and I'm going to talk about the actual results of applying strain to this material. So let me briefly comment on the methodology. So we are using this device, which nowadays you can also purchase commercially, but we build it ourselves. So this was first pioneered by Cliff Hicks in Andy McKenzie's group, and which they basically utilizing 3 piezo stack that control the motions of 2 aluminum plates. And then when you're going a crystal across this aluminum plate, then either you're moving the plates away or moving the plates closer together, you're applying strain up to 1%. So obviously there are many ways to applying strain to the material. And then a lot of experts are in the audience. And then for example, like Peng Chen and Stephen Wilson, they have developed this technique of applying uniaxial pressures and then doing neutron scattering experiments in situ. Now, I think the advantage of this method is that you can apply in both tensile strain and compressive strain. So basically, both positive and negative pressure in the same time. And then this will turn out to be useful in determining the nature of the observations we made. And now, obviously, you can also apply positive and compressive strain using the method that I just mentioned a few slides before, the elastoresistivity resistivity technique by gluing the crystal on the piezo stack. But just due to the nature of the piezoelectric materials property, the strain you can apply is of the order, it's definitely smaller than 0.1%, and at low temperature it could be even lower. So, this is a really useful device and technique to study the quantum materials. So let me start with the material that already have a nematic phase and already have an antiferromagnetic phase, a composition around this part of the phase diagram. So on the right is the resistance versus temperature of this material, where you can see that as you cool down the resistance, first you see an upturn corresponding to the structural transition anomalies, and then like inflection points that corresponding to the antiferromagnetic transition temperature, and then finally a drop at the TC around 13 Kelvin. So so now we started to applying strain to these materials, which is and then plotting the resistivity versus temperature below the 20 Kelvin on the left-hand side. So the strain state is color-coded, and the red string corresponding to very tensile strain, and then the blue color corresponding to very compressive strain. So what you can see is that, first of all, in the yellow and green region, which is the smaller strain range, you don't see a lot of change of TC. Now, the resistance versus temperature, they drop approximately about the same temperature, 12 Kelvin. However, if you look at the normal state resistivity, then the normal state resistivity changes a lot. So the reason for that is because you're already in the nematic states, and then you naturally form in nematic structural domains. So the effect of strain in this range is really just aligning this structural and nematic domain. So therefore, this large change of resistance is really just aligning domain either along the resistive directions or perpendicular to the resistive direction. So what you see with this large change of resistance is really just the large resistive anisotropy of the structural nematic domains. But once you fully saturate the domain and then fully polarize the domain, and then you further applying strain, then you're starting to actually distort the lattice and then pushing the resistance versus temperature curve towards the left. And to make it more obvious, then we plot the resistance in the log scale. Then you can really see that this resistance eventually drop into a noise floor at some temperature, but this temperature is being pushed further and further away to zero temperature for the either compressive strain or tensile strain. And then in fact, at the most compressive or tensile strain, even though the resistance is dropping almost linearly in log scale, but if you extrapolate this linear curve all the way to zero temperature, then it reaches to a finite but small value. So in essence, we're actually achieving a metallic state in zero temperature with this strain states where you have measured finite resistance instead of zero resistance. So so if we track, I think there's a question.
Yeah, can you say why the transition is also becoming broader? So basically this suppression of rho, it almost traverses 10 Kelvin or something. So why does strain make this?
Yeah, so this is a great question, because this is actually what I'm going to talk about this slide. So okay, so to answer your question, first of all, let's first define, for example, the zero resistance state as TC, and then plot this TC as a function of strain. Then you can see that this superconducting phase boundary is actually forming like a dome shape, where the peak of the dome is at the center, at the zero strain state. And but once you pass this, initially you have a rather flat response to strain, but once you pass certain strain, then this TC drop very significantly as a function of strain. So the measurement, what we're doing now is we're applying a constant strain and then cooling down as a function of temperature. So we're doing a vertical cut of this phase boundary. So and you can already see that if there's some uncertainty in strain here, then you can have a very large uncertainty in TC, which is probably why we are observing a very broad transition in this in the RP system.
Actually, do you actually see much of a difference? When you put string on, your TN shift as well, and TN TS. I mean, you no longer have a TS, right? So how much TN? How much TN has shifted? Between compressive and tensile strain.
That's a very good question. I unfortunately didn't make a slide about this, but I think the TN, within the strain range, TN has been shifted to probably 10 to 20 Kelvin or even larger. Yeah, that's quite a lot. Yeah, but there's a caveat, which is we determine TN from R versus T in the fixed strain curve, and to be honest, I'm not that confident of really determining. Yeah, because this in zero strain state, this peak is really sharp, and then really just the anomaly of the resistance dRdt versus temperature looks just like the heat capacity. But as you apply more and more strain, then obviously the TS, the anomaly has broadened and smeared out. And then also, although we're still observing a peak, but I mean, to me, it's becoming more and more questionable to using that peak to identify that as T nil. So, if we can, for example, combine with your neutron experiment, and that'll be great to actually very, quantitatively map out this phase diagram. Not just
actually, my curious question is whether, I mean, is the magnitude similar between compressive and tensile strain in terms of shifting in Tn?
So the interesting thing is that the anomalies actually almost disappear when you're tensile stranded crystals.
I see.
So it's basically looking like almost a flat straight curve as a function of temperature for this. So presumably, I mean, the compressive and tensile, they should do the same, right? I mean, they're all triggering this anisotropic strain. But,
I mean, I guess I was just curious whether you can essentially think about the, you're actually using this pressure as a way of shifting the phase diagram, because your Tn has shifted, right? You basically shift the whole phase diagram.
Yeah, exactly. Yeah, I think that's how we view this as well. This is basically a third axis in the phase diagram, which I will talk about that. But you're kind of already, we kind of already.
Sort of related to that, if I just try to get an orientation, if one uses the uniform isotropic pressure of similar magnitude, does it change TC by similar amount or negligible amount?
Right. So again, I don't have a slide for that, but I actually have a slide from another talk on this. For a similar compound, you probably need like 5 or 6 GPa in order to achieve the same amount. And it's a bit, I think it's, so first of all, I mean, this is quite larger pressure. And then second, I don't think they are exactly the same, because obviously they belong to different symmetry classes.
Sure, the symmetry is different, but just empirically, you're saying the effect is quite different with the two kind of pressures.
Well, curiously, the RFST actually looks quite similar. They're also showing, I suspect, I mean, it's probably doing somewhat similar things, right? Like when you pressure, it kind of shifting the whole phase diagram towards more underdope, and then therefore you're enhancing the nematicity, and then But I think the effect is very different for optimal dope, which I'm going to show that in a few minutes. Okay, so there was the question of why the curve is so broad, and then I think part of the answer is that it is we're cutting vertically on a very steep phase diagram. So now, motivated by these questions, and then also just from a technique or from application point of view, it would be nice if we can sit at the same temperature and then switching the superconductivity on and off. So we did this experiment, at each temperature and then sweeping strain. And also, in order to make sure that we're not really just suppressing a tiny part of the crystals and then creating resistant states, or we're actually inducing a bulk phase transitions, we're measuring, so therefore we do a measurement of the magnetization versus strain at a fixed temperature. So this is using the neutral inductance method to measure the magnetization of crystal under strain. And so at low temperature, which is the green curve here, so in zero strain, you see a very large negative response. Now this is coming from the Meissner effect. The superconducting state is screening the magnetic field out of the crystals. And either applying positive strain or negative strain, you can drive the system out of the superconducting state, and then the Meissner state goes away. So you see a large increase of the magnetizations, and then eventually, the strain you require to push this out of the superconducting state become lower and lower. And then, of course, once you go to high temperature, then you're in the metallic states. You no longer have the Meissner response. So this further confirms that what we're seeing really is not just some weird conducting path on the crystal, but really this is a bulk phase transition of the superconductor. Now, just as a side note, we are also doing a resistance versus strain measurements, which here, you can also see that simultaneously while you're driving the system out of the Meissner states, the resistance also increase from the noise floor and all the way to the normal state value. And then you can see that there's a huge modulation of resistance, which there's like a 4 orders magnitude of change of resistance as you applying strain. And very interestingly, this curve, reminds me of the kind of curve you observe when you're doing, you know, for example, like measuring a field effect transistor, where this is the gate voltage, and then this is the drain source current, and then, but here, no, this is opposite, right? So in the transistor, what you're measuring is the conductivity, well, actually going from 0 to finite when you're gating the samples. But here you have a superconductor where your resistance going from 0 to finite as a function of strength. Yet the shape of curve looks, you know, quite similar. Okay, so with all these data sets, we compile the phase diagram of these underdoped samples, where this blue boundary is the Meissner state, which is enclosed by this black boundary, which is the zero resistance state. And then outside the zero resistance state, there's actually a region where the IV curve is still nonlinear. So we characterize the IV nonlinear exponent, the IV exponent in this color map, where you have an exponent that is different from 1 and then close to this zero resistance states. And then eventually, when you apply enough strain or go to higher enough temperature, then you're folded back to the metallic states with the linear IV. Okay, so this is the underdope. Now, obviously, the question is, and in fact, this can all be, interpreted in terms of competing order, where you're just increasing the antiferromagnetic order, and then, as Pengchen mentioned, increasing T-nail and then gapping out more carrier density. So what about the optimal doping? So for optimal doping, we choose this composition 7% where there's no long-range magnetic and structural order. But still, we're seeing a very large suppression of superconductivity with strain. And this is the resistance versus temperature curve. And again, with both tensile strain and compressive strain, the TC goes down very quickly from 25 Kelvin all the way to 5 Kelvin within about 1% of strain. So this very strong suppression was gradually goes away if you go to further, overdoped samples. For example, like this 10% overdope, where the TC actually only decreased by a little, from 25 Kelvin to 22 Kelvin. But with the same magnitude of strain, the TC only decreased from 22 Kelvin to 19 Kelvin. So much smaller suppression in comparison to optimal dope. And then eventually, when you go to the very overdoped, even more overdosed samples, around 11%, and with a TC around 17 Kelvin, then you don't even see this symmetric suppression for both compressive and tensile strain. What you see is that the TC just linearly change with strain, and this is more like the pressure effect, where when you're squeezing or pulling a crystal, it's the A1G symmetry mode are controlling the TC. So together with all this doping dependence, we fit this quadratic coefficients for the low strain data, and then use that as a way to quantify the strain sensitivity, which is this alpha term here, these 3 data points. And with these other 3 data points are the nematic accessibility measured by the 2 and 6x. And then you can see that this strain sensitivity is much more sensitive, has a stronger doping dependence compared to the nematic accessibility. And in fact, this kind of measurement has been discussed in a recent theory work by Sam Lederer, Erisberg, and Una Kim. They are considering a different system, but the same idea is that if you can use strain as a way to measure the change of TC and then correlate that with nematic accessibility, and then this could be a test, like the isotope test to test the paramechanism of the superconductor. And one thing they pointed out is that because this strain sensitivity is, ultimately it will be proportional to the nematic accessibility square. So therefore, we do expect a stronger doping dependence for strain sensitivity compared to nematic accessibility. So before I closing this section, let me just give a few outlook to this. Oh, well, okay, no, there's actually one more slide. So I also want to put this into a context of how the strain sensitivity compared to other superconductors. So we compile the strain sensitivity defining by the largest change of TC versus divided by TC, and achieving by strain, and then plot it against TC for various superconductors. So you have cuprates here, and then you have some traditional superconductor, tin, niobium 3 tin, and also niobium selenide. And then you also have stronger ruthenate here. So basically, the cobalt-doped barium-122 have a strain sensibility that is above all the other superconductor except for strontium ruthenate. And in the case of strontium ruthenate, it's an increase of 1.4 Kelvin to 3 Kelvin, with also approximately amount 0.5% of strain. Okay, and then finally, this very strong sensitivity allow us to construct this three-dimensional phase diagram where the T, as Pengchen pointed out, Tn increase, and then also we can reach another quantum phase transition by suppressing the superconducting dome all the way to 0, and then achieving a superconductor metal quantum phase transition in a three-dimensional material. So a few outlook, and so first of all, an obvious question, elephant in the room is that what is the role of spin fluctuation? We always have this antiferromagnetic phase in these materials, and then spin fluctuation has been considered as the leading candidates for the pairing of this material. And in fact, with the strain, the T-nil increase, here I'm citing one of the Pengchen's paper where you see the T-nil increase by pressure, and also from the from Nick Kroll's MMR measurements as a function of strain, they also see that the spin susceptibility, the spin fluctuation actually increase as a function of strain, both tensilely and compressively. So that basically implies that, at least for the optimal doping where there's no long-range magnetic and structural order, when you're applying strain, you're not only suppressing the nematic fluctuation, but you're also increasing the spin fluctuation. But still, the superconductivity is still suppressed by strain. So does that imply that the nematic susceptibility is playing a more important role, or the kind of spin fluctuation already changed fundamentally as you're applying strain, and then therefore no longer helpful for superconductivity? No, we don't know.
Yeah, so recently we found that when you put a string on, the magnetic structure actually changes as well. You actually induce a C-axis moment. I mean, yeah, this is for Nick Kroll's work. Yeah.
Mm-hmm. Right. So this could be, this could be the reason, right? The intensity, not just the intensity matter, but also the type of the spin fluctuation really matters for superconducting pairing. Now, obviously, to answer the question, one can answer that by measuring iron chalcogenides where there's no longer magnetic phase around. At least there's no longer magnetic phase. And then in this system, both in Shibuchi's group and then also my group, we have demonstrated that there is a very strong nematic susceptibility. So they have found out that very strong nematic susceptibility in the sulfur doped iron selenides. We found out there is a nematic susceptibility divergence in the iron telluride selenides. So it will be interesting to test if you can also see a suppression of superconductivity. So we have some preliminary measurements, and then the effect is definitely not as strong as necktie, but as we see the neckties, a very careful doping dependence is needed to actually get the whole pictures. So the third outlook is that what is the outlook of the what is the nature of this strain-tuned superconducting transition? I think this is quite exciting direction because in the past we only have one way to continuously kind of turn off the superconductivity for bulk material, that is, which is using magnetic field. And now we have a new way to continuously switch the superconductor out and off. And then very interestingly is that near this superconductor metal quantum phase transition, this very broad transition where we see a linear temperature dependence in the log of resistivity actually have also been seen in the superconductor insulated transitions in two-dimensional system. This is a work done by Bob Dyens on a granular lead film where they have some lead islands and then repeatedly deposit some silver films to provide conduction between and Josephson coupling between the lead film. So the whole system going from insulator and then gradually eventually becomes superconductor when there's enough coverage of the silver film around the lead island. And then in between this transition, they also see a log of resistance change linearly as a function of temperature. So perhaps that also implies that we also have some strong inhomogeneity of intrinsic electronic inhomogeneity in the system that just behave like a superconducting islands and that just doesn't couple to each other. So I think that's a very interesting direction to explore. So okay, so I think I only have probably 15 minutes left. Let me try to cover the last part of the talk, which is a new technique to study the new transport coefficients in the broken rotational symmetry phase. So all this past result motivate us to really further look into this process of strand detwining or stranding the iron-based superconductor. So working with Phil Ryan, Jiun Wu, and Jian Liu, we have developed this sample environment where we mount the razor bill strand cells on the X-ray diffractometers. And so a typical measurement like this. Now we have a match seed samples mounted across the two sample plates, and then we are measuring transfer simultaneously. And then using a grazing angle, we can actually measure a large portion. Basically the area of the samples where we're performing the voltage measurements. So let's say we're measuring under those samples, and then below the structural phase transition, you'll form structural domains with some domains aligning this way, and then some domain aligning the other way. So therefore, in the X-ray diffraction curve, now as you can actually see that the one X-ray diffraction peak is split into two. This is because you see two lattice constants corresponding to two domains. Now, let's say we are sitting at this fixed temperature, and then we started to applying strain along the matchstick direction. Then what you can see is that as a function of strain, which is the X curve, this strain is this is like a microscopic strain measuring by the strain gauge, the whole deformation of the samples. And then you can see that as you increase strain, then the two diffraction peak gradually become one diffraction peak. The intensity of one peak is suppressed, and then the intensity of the other peak increase. Now this is basically aligning domain, and then when you're further applying the strain, then you can see that the diffraction peak started to move in the 2 theta or d-spacing, and then you can see that it moves linearly with the strain you apply. So now we're distorting the crystal. So just by looking at this peak, already kind of answer some of the questions that we had before when we were doing this superconducting study. For example, we worried that the strain was not very homogeneous. Therefore, for example, that broad transitions, and then is corresponding to some part of sample is being heavily strained, and then the other part of sample is not being strained. But if you just look at the X-ray diffraction peak, you can see that the width of this peak is not significantly wider than the width of the peak in the center in the zero strain state. So therefore, in this region of the samples, the strain is quite homogeneous. So with these measurements, we can now go back and then check whether this whole idea of distorting the crystal is actually truly suppressing the superconductor. So we plot the orthorhombic distortion, which is the red curve, as a function of nominal strain. And then you can see that there's a range where we're just detwining the crystal, so the orthorbicity is unchanged. But then you can further distort the crystals, and then you start to see the increased orthorbicity for both compressive or tensile strain. And then only once you pass some critical strain value, you start to see that the resistance, which is the blue curve, going from 0 to non-zero. So in addition to measuring this superconducting and lattice response, we're now also to do the measurements we have done a very long time ago, but now doing that in a more precise fashion, which is detwining the crystal and then measuring the spontaneous resilient isotropy. So this part of the figure you have seen already, but now let's say if we plot the intensity ratio of these two, and then we can basically plot a domain population as a function of strain, which going from fully A domain this way, and then or fully B domain the other way. Actually, sorry, the other way around. Fully A domain this way, and then fully B domain this way. And then this black curve is the resistance versus strain curve. So you can see that even if we fully detwin the crystal, it's very hard to tell whether just from resistance alone that we have already detwined the crystal, especially in this part of the region where we detwin the crystal, but the resistance is basically a very smooth curve across this. So it's only with the help of X-ray diffraction, we'll be able to know that we're only detwining the crystal, but not actually further distorting the crystal lattice. So we're interested in measuring the spontaneous resilient anisotropy in the crystal, which means that we want to measure the crystal in a state that is just fully detwined, but not being fully strained with the external stress or external pressure. So we're carefully monitoring this twin population where we're just reaching the full detwinings, and then but without change of lattice constant, and then identifying the row A and then row B where one corresponding to the resistance at this point and one corresponding to resistance at this point for each temperature. Now we can plot the rho A and then rho B as a function of temperature in the strain-free single domain states. So you may say that this determining measurement has been done 10 years ago, but there's a big difference. For example, like this measurements done in 10 years ago with the actual pressure, you can see that the resilient anisotropy is already developed well above the phase transition. And this, of course, is because we're already applying the pressure, the crystal is already being deformed. And therefore, you're already seeing a mix of the elastoresistance plus the spontaneous resilient anisotropy in this part of the phase of the system. So here now we can actually really probing the spontaneous resilient anisotropy and plot it as a function of temperature. So we define the resilient anisotropy as rho A minus rho B divided by rho A plus rho B. And it turns out that this temperature dependence of resilient anisotropy looks just like an autoparameter, a mean field autoparameter with a square root temperature dependence. And this looks exactly the same as the structural autoparameter, where you have structural distortion also have a mean field like temperature dependence. So this same temperature dependence and the same behavior is actually expected from the mean field derivation if you believe that resilient anisotropy is a good proxy of the nematic autoparameter. So in this free energy where you have the nematic autoparameter as the primary autoparameter and the strain as the secondary autoparameter, what you expect is that this you will have a spontaneous strain and a spontaneous autoparameter. They will have a ratio. And this ratio is actually the same number that corresponding to the bare nematic accessibility at the transition temperature. So remember that I mentioned previously that the bare nematic accessibility will not diverge, but will reach to a finite value at the phase transition temperature. It turns out that that number is actually exactly the same number of the ratio of resilient anisotropy, the ratio of the primary autoparameter, the nematic autoparameter to the structural distortion. So therefore, if the resilient anisotropy is truly a good representation of the nematic autoparameter, and then this whole framework of free energy works, then we will expect that the ratio of these two quantities will be the same as the elastoresistivity coefficient at the transition temperature. So therefore, measure the elastoresistivity coefficient of the same temperature of the crystal from same batch, and then the answer is that they do match. The ratio of this quantity is around 150, and then if you look at the elastoresistivity, it basically also reaches about the same values at the transition temperature. So that really means that the resilient anisotropy is really, you can really consider it just like a nematic autoparameter, and then also that the mean field free energy works. So with this correspondence, this allows us to kind of go to over more doping without actually measuring the spontaneous resilient anisotropy and the spontaneous lattice distortion. If we now know that the finite value that you reach with the elastoresistivity coefficient is actually just this just this value, spontaneous elastoresistivity coefficient, which we define as spontaneous elastoresistivity coefficient. Now, what is the significance of this quantity? If you think about this, for every Q equals 0 broken symmetry states, there's always some new transport coefficient emerge. In the case of ferromagnets, it's the spontaneous Hall resistivity. For example, like in this ferromagnetic material, you can see that the magnetization versus field just look like the rho xy versus field. Now we also have another Q equals 0 symmetry breaking phase, the nematicity, where you have the transport coefficient looks just like the thermodynamic overparameter. And we know that the anomalous Hall coefficient, which is defined by this transport coefficient divided by thermodynamic overparameter, which is magnetization, give you a lot of information about systems, such as Berger curvature. Similarly, we believe that for the resilient anisotropy and the spontaneous lattice distortion, the ratio of these two will also give you similar amount of information, which is telling you the electron lattice coupling. So now using this, this is basically what I just said, and using this correspondence I mentioned before, we now look at re-examining these elastoresistivity measurements before, and then you can see that the value of elastoresistivity coefficient at the transition temperature actually increased quite a lot as you reach into quantum critical point. So that basically means that the spontaneous elastoresistivity coefficient is also increasing by the same amount, if the mean field framework works until you're reaching the quantum critical point. So looking back to this color map, now I think there's actually more information hidden within this map. So you can see that this elasticity coefficient is really strong around optimal doping, but this is not just saying that the nematic accessibility is stronger at the optimal doping. It's also saying that the lattice coupling is enhanced. So if you're considering the nematic accessibility, it will diverge as you're approaching the critical temperature. So obviously, you will naively you will expect that you will see the same intensity going from this underdoped side all the way to the overdoped side. But still, you're seeing the intensity increase as you're moving toward this phase boundary. So I think that basically means that there's a combination of divergent accessibility, but also a divergent electron lattice coupling. So finally, I just want to say that in addition to the cobalt barium 1 to 2, there's also nematic accessibility measurements for other systems, for example, 1111, and then also the iron chalcogenides. And then intriguingly, I think all the systems that behave very similarly. That is, you can see that the M2M66 not just diverge as a function of temperature, but if you trace along this phase boundary, they are also seeing an enhancement while they go towards the quantum critical point. So this behavior could be a very generic phenomenon of a nematic quantum critical system. Okay, so I'll just leave my summary slides here, and then I think this is the end of my talk, and then I'll open for questions.
I'm going to clap for on behalf of everybody. Thank you, Jiun Haw, very much for such a fantastic talk.
Very nice talk, yeah.
Any questions? I know we already asked a lot of questions.
Yeah, so I'm curious on the on your assessment of the iron selenide. I mean, you argue that there's a string can tune TC. So have you tried iron selenide? What happens? There it's much cleaner, right?
Yes, there is much cleaner. There's no magnetic phase. We haven't tried that, but I know Cliff Hicks have already tried that, and then the rumor is that it's not changing a lot, and also you can also kind of infer that from Anna Boehmer's measurements, where they measure how the orthorhomicity change when you enter in TC. So for cobalt barium 1 to 2, the orthorhomicity decrease a lot when you enter in superconducting states. But for iron selenide, the orthorhomicity change almost doesn't change when you go across the TC. So that already kind of implies that there won't be a lot of suppression, because this is basically a thermodynamic relationship that works both ways, right? Right. But yeah, again, that's just pure iron selenide. I don't know what will happen here, and I don't think anyone has, at least to my knowledge, no one has actually measured here. And also the other side, which is by tellurium doping, we have measured a tellurium doping that is, I think, can be considered as the overdoped. So we have measured somewhere here. So here, the iron selenide is somewhere here, right? And then iron selenide corresponding to x equal to 1 here. And then the nematic phase is being suppressed along this direction. So this is basically the overdope of the nematic quantum critical point. And we also didn't see a very strong suppression. I mean, there is suppression. You can clearly see this symmetric change of the TC. But it's definitely not as strong as the optimal dope or the underdope of cobalt barium 1 to 2.
So I would argue, yeah. I would argue that I mean bodes well to the idea that instead of the nematic phase competing with superconductivity, it's the antiferromagnetic ordered phase, static antiferromagnetic ordered phase, because everything that when you see in the underdope regime, the reduction in lattice parameter below TC is actually accompanied by the reduction in the static ordered moment below TC as well.
Right.
So it's really a coupled. It's a coupled transition. So just nematic phase itself, may or may not suggest that, it's directly competing with superconductivity.
I think this is a very likely situation, but also, I want to say that we also see that in optimal dope, where we don't really see any evidence of the onset of a static antiferromagnetism as a function of strain, but still the TC is still quite. So yeah, I don't know. My personal feeling is that this is probably the kind of question that very that depends on which part of phase diagram and then specific mechanism, and then so it's not like a clear-cut answer that spin fluctuation is the prime period mechanism, or nematic fluctuation is the primary mechanism. I think it could be very complicated interplay, and then but at least now I think this this is a way to very quantitatively and very carefully address this question.
Can I just quickly jump in on this one? So in terms of spin fluctuation, I guess, do we know how much spin fluctuations there is in the iron selenium ones compared to the optimal doping of these 1 to 2?
Oh, no, I'm not talking about spin fluctuation. I'm talking about a static magnetic order. Because in all the samples that Jiun Haw looked at, I mean, there's always a static magnetic order. Static magnetic moment always decreases. You know, always enhancing when superconductivity occurs. So it's direct competing with superconductivity. Whereas in the overdoped sample, there's very little static and long-range magnetic order. In the case of iron selenide, there's no static order at all, right? But spin fluctuations are there.
Right. So so the strain. So you mean the strain in those cases don't enhance the spin fluctuations in iron selenium?
Spin actually enhances. I mean, we actually have shown that when you put pressure on, your anisotropy, pneumatic anisotropy actually changes. Spin fluctuation actually changes, shifting more from the O1 side to 1O side. So there's a direct coupling, yeah. But
then you don't see any effect on TC.
TC also changes. I mean, it's always coupled, right? I mean, but TC changes are, you know, the amount of strain we can apply is rather small. TC changes are, you know, yeah, small amount.
I think Pavel, you have a hand up.
I have a question about the normal state. So did you study something like non-Fermi liquid signatures, and how do they depend on strain?
So which non-Fermi liquid signature are you?
Well, I mean, let's say the resistivity versus temperature, or whether it exhibits some non-T-squared dependence, right? And how these power laws near the quantum critical point are affected by strain.
Yeah, this is a very good question. And yes, we have some studies, but we don't have any conclusive results yet. But one difficulty, let me say this, one difficulty is that once you're applying strain, then now your resistivity is basically anisotropic, right? And I guess now, how do you define the power law in this sense? I mean, most of the time, people considering the power law of resistance, you know, considering the overdope case where things are isotropic. But here we actually have an isotropic resistivity tensor. Of course, you can divide the average of the resistivity as the resistivity to compare. You know. But again, once you applying strain, you're already inducing some static nematic order. So therefore, it's not. I mean, it's not clear that to me that you can actually make a direct comparison to the kind of non-Fermi liquid theory people did before. For example, like when you apply strain, you already see an onset of the. What you see is that the resistivity will actually have an upturn, even for the average resistivity, will have an upturn, going from linear to showing an upturn as you're approaching the superconducting phase.
Upturn, so it becomes more resistive on cooling, or
on cooling, yes, on cooling.
And it is just the effect of it can be effect of domain. So what do you attribute it to?
It's not the effect of domain. I think it's the effect that the system is more resistive in the nematic states. So this is the part that I haven't really talked about, but for example, like this elastoresistance curve I show you, right? So I show you how rho xx minus rho yy is respond linearly as a function of an isotropic strain. But in the same measurement, we also show that the rho xx plus rho yy actually responds quadratically as a function of strain. And the quadratic coefficient is positive. So that means that when you're making the system more anisotropic, simultaneously the isotropic average resistivity also increase. Now, I don't have a full answer for this, but my interpretation is that this is evidence that the nematicity is deeply related to spin fluctuation, because when you either increase or decrease strength, then you're enhancing nematicity and increasing spin fluctuation, which increase the scattering and therefore increase resistivity.
Thank you.
You're welcome.
Maybe we'll just have allowed 2 more questions. So Doug, I think you had your hands up first.
Yeah, thanks. Very, very pretty talk. Quick question. So when you were comparing to that old work from Dines, this your sort of anomalous metallic state. You may have already said it and I may have missed it. I mean, so do you think that there is basically still, do you think that there's still pairing going on there? There just isn't sort of global superconductivity?
Well, I don't know. I mean, so let me say, I'm an experimentalist, right? I can only tell you operationally, how in the past people have defined the anomalous mental phase, right? There's big drop of resistance, which orders of magnitude drop of resistance compared to the true metallic state.
Okay.
Right.
Okay.
There is also.
And what's the magnetic susceptibility doing there? Is there still a lot of diamagnetism?
There is not a lot of diamagnetism. But although we're measuring the mutual, we're using the mutual inductance. So this is not a very super accurate measurement like the squid. Sure. So yeah, I cannot say. I mean, no, but you can also notice that they recover, but that doesn't really fully recover to the full normal state value. So I think a more quantitative, precise measurement is needed to address that, and then that's the direction we're working on.
Okay, thank you.
You're welcome.
And then Han Yu.
Oh, yes, thank you very much for the nice talk. I have a very, very naive question. So for the nematic order, can I just understand it as the electronic state coupled with, say, omega equals to 0 phonon mode, like the B2G modes that you're talking about? Is there same or what's the difference?
So, right. So obviously, a deformation of the electronic system will couple to the omega 0 B2G phonon modes, which is basically an isotropic strain. Now the question is that let's say if you really turn off this coupling, or somehow you can have a fictitious system where you fix the strain to be 0, so that the system doesn't move, does the electronic system still spontaneously trying to forming an isotropic state? And I think if in this case it still does want to do that, then I will consider it as an electron-nematic phase. And the iron-based superconductor is one of them, where you can measure this you can show this by doing this elasticity measurements, where you measure the response of the electronic anisotropy, which is receiving anisotropy at a fixed strain, and they're still showing divergent behavior. So that's how I would define electron-nematicity. The microscopic mechanism could be very different from one system to the other. For example, it could be coming from local ferroquadruple orders, or it could be coming from the spin fluctuations, for example, like in the iron-based superconductor, fluctuating density wave. But I think the spirit is that there is a true instability in the electronic part of the free energy.
Because in this case, even if we fix a strain, so just say clamp the sample, there's no way to stop the structural fluctuation, right? So it still somehow coupled with the electronic anisotropy. Is there a way to control that parameter?
Yeah. So that's how the elastic system do, right? So you're right that if you fix the system, there could still be structural fluctuation. But let's say if you strain a crystal, you're basically suppressing a structural fluctuation by forcing the structure to be strained in a certain way. And then while you're doing this, you can ask a question: does the electronic still becoming more and more anisotropy as you're approaching, as you're lowering the temperature? And if it does, then that means that the electronic really has an instability to go towards a phase transition. So
I see. Because in your case, you kind of demonstrate that by applying strain, the TC goes down, right? But the nematic order doesn't go down.
The nematic order, when you apply strain, then obviously you already break a system. And nematic, the nematic transition become a crossover, right?
Oh yeah, that's right. Yeah, there's no way to distinguish.
Yeah.
All right, thanks.
You're welcome.
Any last burning questions before we let you have a rest? If not, let's thank Jiun Haw really very much for this very beautiful talk.
Thanks, everyone.